I should have put this in the previous video while we were still on the topic of optimizing adders. So I guess this is going to be clarifications corner. The product of nibbles is a level I could and in fact already did optimize. Quite simple. This was multiplication. Multiplication doesn't matter for us right now. What matters is we used to have 3 adders in order to add these 4 quote-unquote bytes. But of course, none of these are actually full bytes. They are all 4 bits, except each 4 bits are shifted. And so this is something of an interesting wiring project to reduce. Well, I won't bore you with the details, but this is my final result. 8650 as opposed to 184, 194. So this is quite efficient. And something of a slightly interesting idea here is the fact that I am trying to balance, just like we discovered last time, I'm trying to balance the sizes of these 3 things. These are essentially the 3 adders that we used to have, except now they are in slightly different order, right? So first I add up these 4 bytes, or these 2 bytes, and in parallel, I add up the last 2 bytes, and then I add up the sum of, well, both sums together with this final one. And this is only one way in which this could be done. And I think this is the optimal delay score, or at least close to it, simply because of how I parallelized it. It would be possible to, for example, in fact, I was quite tempted to do this. When we have this byte, which only has the first 4 bits, right? And we have this byte, which pretty much just has the 4 last bits. They can be combined into one, pretty much. And then I can use this one full byte for some addition. And then what's left is these things, which would also need to be added separately. But I think that would result in an imbalanced adder. And that results in a larger delay score than this. So, yeah, again, I'm not going to go into all the details. You recognize the basic idea. This is an adder. It's just gutted and reduced with all the knowledge I have about 0 bits and non-existent bits. Same thing here, then same thing here. They are shifted here, so they are not directly... These bits don't directly align with each other, but they are aligned in the final adder, so that's that. And yeah, just to drive the point home, again, the delay score in this is 50, which is almost a quarter of what we had originally. So it's not just that I removed these adders, it's not just that I reduced them. The delay score is... yeah, if I were to remove 2 adders and just leave 1, I still wouldn't have that delay score. Well, still wouldn't have a delay score as good as what we actually got. So essentially, in the end, I am sub 1 adder for these however many bits. Actually, these are... Oh, that's very curious. I just realized. We have 4 bits in every byte. So in total, this is 8 bits and then 8 more bits. So essentially, we are adding up 16 bits. But because of their strangely shifted positions, these 16 bits being added, 8 plus 8, is not even as complex as a single full adder. Although, what's up with the gate score on this? Yeah, the gate score is slightly larger than a single adder. 56 to 86. I wonder, 1, 2, 3, 4. Yeah, so this is 16. I wonder where the 14 comes from. Couldn't be bothered to figure this out. So, yeah. I've already spent way too long on this. this is Clarifications Corner. Actually, one more thing for Clarifications Corner. This level, RAM. This is not how you build an ASIC. We're not using all the power of this RAM, we only needed 32 values. Just because the level name, the level title says RAM doesn't mean I have to use an actual RAM component. This is a lot more like how you build an ASIC. In order to save 32 values and then output them in the same order, it's enough to just delay the values by 32, and this will effectively save them. So yeah, what I have is just a huge delay line. Like this. Now, there's a slight... This is satisfying to watch. There's a slight issue with this. Something I dislike is this single line, 1-bit line. This is necessary in order to know when to actually enable the output, and this is essentially just a 32 delay line from this on. But this feels redundant. I could consider using just a counter, but counters are kind of expensive. I might, but somewhat more interestingly... Oh yeah, by the way, delay score of 0, because apparently a delay line has no delay. Yeah, so as I was saying, I could use a counter, which I might try, but somewhat more interestingly, I feel like, this is just intuitive, but I feel like there must exist some kind of solution to this that uses some clever combination of delays. And this reminds me of the Busy Beaver problem, I believe, where people compete in trying to come up with the shortest program that runs for the longest time, but that does still terminate. So not infinite recursion, or not infinitely running, not an infinitely running program, but a program that takes, you know, however many gajillion steps to terminate, but still terminates in the shortest amount of code. And so it feels like I should be able to come up with some combination of delays that somehow loop into each other. So like, I don't know even how to begin, but you know, just like this goes back into here, but then maybe there's like a knot somewhere, and then, come on. Right, then this is a knot, and then, I don't know, this goes all the way back over here somewhere, and then, you know, the state of it will grow in certain increments, like this will light up, then this will light up, then we would have to proceed over all combinations of loops glowing. I have no idea how to actually make this, but it feels like there should be something like that, but I just don't see it. Yeah, the counter approach is cheaper in terms of gates. We had 288 and now it's 282, but because it introduces some delay, this is not worth it. So yeah, it still works, but it's not good. And yeah, I've given some thought to these loops, and so far I cannot exactly come up with anything. This kind of feels relevant to the solution that I suppose exists. I've never seen, but I've heard that people were able to solve the maze using 2 gates. So I assume that's a huge mess of wires and not costing any gates, but they must have somehow been able to make those wires behave in some smart way by just connecting them. And this is kind of what I have just described with the loops on the delays. But yeah, so far I don't see anything, and I don't want to spend all that much time on this for now. So yeah, I think I'll just call this my RAM ASIC, and the rest I'll leave for later still. Oh, and also a cheaper way to make this counter work. Instead of having a 5-bit counter, and testing for equals 31 and then remembering it with the delay contraption, what I can do is I can just use a 6-bit counter. And while this thing is slightly larger, by saving gates on the the comparison and the saving of the state, I can just use bit 32, and that saves me some gate score. This does have slightly larger delay, but overall this is cheaper than my original 5-bit counter approach, but still more expensive than the 32 delay line. So yeah. We are inching ever closer to completing the game fully. Just one level left. But I'm still not gonna do it. Not today. I just want to finish everything. I don't remember if I said this. I think I must have repeated this 15 times by now, but yeah, I want to finish everything, optimize everything else, everything I have to the best of my ability, so that by the time we are done with the game, everything else is also in order. I'm kind of hoping there's some secret level up here, which is gonna unlock once I complete everything, but we'll see. But before AI Showdown, which I left for last, there's still a couple of things we need to do, and that is mainly ASICs. Just looking at the scores here, I've already done all these, but we still need to do Delicious Order and Waterworld. What's up with this? Unseen Fruit. That's not graded for some reason. This is yeah, this is this one where you need to keep track of which fruit you've seen. Huh. I wonder why this isn't graded. Do I wanna do this one as well? How complicated is this ASIC? Is this just... I don't know. But sure. I wonder if you can walk out of here. No, you cannot. Wait, can I? Can I interact with this? No. Can I shoot it? Hello, alien friends. A fine bookshelf. What's the number? 47 bookshelf. This is cool. 47. This is completely unnecessary. Alien, hello. Lobert. Earth fruit is so much better than this stew. Stew they normally serve. Oh, wait. I can shoot aliens. Did you know Earthlings eat with their face? Ew. Gross. Don't break the walls. Bad robot. Okay, now we just have to find more walls to break. I'm totally shooting one alien, by the way. What is happening here? Wait. Wait a minute. These are cells. Wait, what? What is happening? That's a little human. Is that me? That's not me. Do I need to program the robot to do all this? I'm genuinely just discovering this, by the way. I didn't look this up or anything. Okay, I'm scared I might do something wrong and everything explodes. Ghoul. Okay, I don't think I want to shoot the aliens first. I'm not sure how important this is, but this seems like a Steam achievement. Okay, control panel. I don't want to press that yet. Let's read sign. It says the button opens the prison doors. I see. Well, there's a guard with a gun, but they don't care. And this looks like Dr. Raku. That's a skeleton-looking thing. Let's read the sign first. Secret lab. Bookshelf. Table. Table. That's a weird table. Okay. Nothing. Barrel. This is a barrel. Yes, thank you. Okay, let's talk to the guard. The guard has a gun. Yeah, prison guard. You're not supposed to be here, Robert. Well, I mean, should be thankful I didn't shoot you. Dr. Raku. I am the esteemed Dr. Raku. Yeah, I figured as much. Okay, can't zoom any further. I assume, yeah, doors are locked. Well, let's open it up. Let's talk to the human. Bad robot. Oh no, I'm gonna get shot. Okay, let's, this is like... Oof. I actually killed the guy. Wait, what happens if I don't want to find out yet. Okay, let's talk to the human. I assume the other critters won't hurt me. Hello, snake. I'm robot. Your poison doesn't... Or venom, sorry, venom. Human, hello. I am the player. What if I kill the player? What happens if I kill the player? Do I want to find out? I'm not gonna kill the cat. I should go shoot the aliens. Wait, talk to me. No, don't run away. Don't run away. I am the player. Can I interact with the snake? Come on, snake. Snake. Hiss, rattle. Any more cracked walls here? We can pet the kitten. Is that a dog? I think that's a doggo. Hello, doggo. Woof, woof, yes. And that is... What even is that? Spider? Rat. Squeak, squeak. Sure. Is this it? I don't see any more cracked walls. I do see that tile down... No. I'm not gonna shoot the rat. Rat, you can leave. I don't remember the binding to chill. Oh, enter. Okay. This looks like a door? But I can't actually reach it, so... What if I press the control panel again? Nothing happens. Shooting doesn't help. Okay, let's, you know what? Let's also shoot the barrel. No? Nothing happens. I wonder if programming some behavior like this, you know, breaking the script, would... Hello. Don't break the walls. How about I shoot you? I'm bad robot. Oh, aliens have force shields or whatever. Okay. Is that it? I think that's it. Yeah, and the guard is back. I'm not supposed to be here. Yeah, yeah. What happens if I get killed? You died. Oh, enter is not enter is interact, not chill. Killed by Dr. Raku. The hearts in the top bar are decoration only. Oh man. Okay, but I can reset and this wall is broke. Wait, do I have to look for her secrets in all robot levels now? Guess I do. Table. Yeah, I'm gonna have to go over all the other robot levels and check for secrets. And I didn't find any. Let's do an ASIC for delicious order first. This was a level where we received a bunch of numbers as inputs and we needed to output them sorted. I don't exactly remember in what direction, in what order. Descending or ascending? Smallest to largest, so ascending order. Alright. My task, and it's 15 numbers. It's a strange number. 15 is not 16. You would expect 16 as your input size. Okay. So I want an ASIC for sorting. Where do I even start? What are my thoughts? I mean, the first thing that really comes to mind is, how am I even going to store these things in an ASIC? There's two options I can use. Again, a RAM component, wherever that is. I can use RAM, but that does have a pretty large delay, and it's quite wasteful in terms of the number of things it can represent versus the number of things I actually use. Right, I only need 15, which is going to be this much in one row. Huh. Oh, and actually, I think there's another issue with using RAM for this. Like, at some point, I will need all 15 saved. Right? It's not possible for me to output them on the fly, and I will necessarily need at some point to remember all 15. However, when I read a new one, the RAM can only work with one thing at a time, which is kind of an anti-ASIC property, to be honest, where in ASIC you can parallelize and you can do a bunch of things in one tick and save a lot of time that way, although that might cost extra. With RAM, it is not at all possible for me to read a number and then perform comparisons on it and do something with it. I would have to literally just read everything into RAM, and then I would have to emulate pretty much. Yeah, so if I am to use RAM as my storage medium, I would have to pretty much just emulate the assembly program that I wrote. I believe I wrote multiple. I would just have to do an assembly algorithm, except it would have to be hard-coded in gates. Which does not sound fun. I'm not saying that would be too inefficient. It might actually turn out to be reasonably good. It might turn out that having... Well, yeah, my only alternative, which, like I just said, might turn out to be quite expensive, would be to use 15 8-bit registers. Or actually, I wouldn't use these. I would use my custom, slightly cheaper base registers. Right, and I would necessarily need 15. So I would need 1, 2, let's say 3, 6, 9, 12, 15. I would need this many, which that's still cheaper than the delay on the RAM, right? And the delay, what's the word? Contributes to the total level score the same way as gate score does. So I really should be mindful of this, I think. And if I remove this, the delay on a single base register is negligible. It's 4. Yeah, so we're not getting to 1,000. Yeah, so this is actually cheaper than RAM, although it would require more logic. If I have a pointer to one of these, I would need a decoder to actually address it. Although a decoder with 15 addresses is also not particularly expensive. I should even have it. Like, is this it? How many is that? Yeah, this should be 16, right? 1, 2, 3, 4, 3, 4. Yeah, whatever. How expensive was that? 45. I mean, a little expensive, but not too bad. Okay, so let's say we've settled on using registers for memory. What do I do now? Well, I'm immediately thinking, unlike with leg and unlike with using RAM, with this kind of setup, I have a lot more easy direct control over my array, right? Because I don't have to move the pointer. And this actually enables me to use an online sorting algorithm. That is, I can immediately insert a new value in the place where it belongs in my array when I read it. I remember thinking about this kind of approach a bunch for my original assembly solution, and I believe I decided against it because the overhead of trying to do something like this in assembly would be way too much. I'm just playing around with wires at this point and thinking. But here, there is no overhead. I can just encode anything I want with gates. So the question is, what exactly do I do? Well, the obvious approach that immediately comes to mind is, of course, just basic insertion sort. And I think it would actually be... I'm not gonna say it would be particularly efficient, but it would be neat. It would be a cool, intuitive, physical representation of the idea with all these registers. So what I could do is just have them literally in a line, and they would be essentially connected like this, possibly with some muxage, but they would just be connected in a line, right? And the first one would be connected to the input, and the last one would be connected to the output. And what happens is, at every tick, I load a value, and it goes into this line. This would be a queue, essentially. And the value at every register would need to be compared to the value currently saved. And if it is, whatever it was, do I need it larger or smaller? Whatever, it doesn't really matter. It would be compared to the value in the register. And based on that comparison, I would decide, does it belong here? And does this one need to be pushed over? Or do I skip and do I go further with my new value? And that would happen at every point, at every register, until some spot for my new value was found. So for example, if I had like 20 here, and we're sorting smallest to largest, right? And I have 20 here, and I read 22. Then all of these would be skipped, 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 skipped. Then I find 20, and then let's say this is 25, right? This means that I need to fall into here. And then 25 gets pushed forward, and so on and so forth. It just continues. And this would be a pretty neat implementation, and it would actually, you know, you can see the intuition of it. We just have new stuff falling into this pile and pushing forward all the stuff that was saved. And then we would keep pushing stuff forward until it all ends up in the output. So it's kind of physical in that way. But this would be pretty expensive, even though it being an ASIC, it's just a single tick. Each of these comparisons will essentially cost me a comparison operator, right? I would need 1, 2, 3, whatever, 15 comparisons. And these are not cheap, 53.22. So I'm not sure if this is in fact the best I could do. But it is tempting. It is tempting. Yeah, so something I've been thinking about now is the possibility for me to reduce the number of these comparison elements I have in my circuit. And somewhat counterintuitively, I think it's actually not possible. Now, when you think about a sorting algorithm, there is generally a number of comparisons value that is associated with it. And this, well, an efficient implementation of a somewhat efficient implementation of insertion sort can actually have a logarithmic number of comparisons. So we would not need to compare everything to everything, but instead, well, we would not need to compare our new inserted value to everything up to a certain point. But instead, what you could do if you were just writing this in code, in C or whatever, you could just apply binary search, right? So try this side, no, doesn't fit, and try this side, okay, try this, whatever. And that would reduce the number of comparisons you would effectively do in C. But for an ASIC, because I do not know which sides I'm going to, right? I don't know if I'm going to be here or here. That means that I do need to be prepared to compare at any point. So it seems like I do need all these, regardless of which comparisons I will actually carry out, and regardless of how I'm going to decide what to compare. Essentially, I need to prepare to compare my new number to everything in here. And I'm still thinking about online sorts, of course. There could be other approaches, but I am really tempted to use online because it's possible here, and with assembly it's just not feasible, I'm pretty sure. Yeah. So if I do need all these comparisons regardless, then I might as well just go for the regular insertion sort and not even try to bother with anything else. I don't see any other way. And of course, in addition to online sort, I'm also kind of focused on doing things in one tick. Because if I were to utilize multiple ticks per new value, then perhaps I could reduce this. Yeah, and I could have maybe one comparison and then just decide which register to load into it in order to compare. Just that could be... I don't know. See, like... I don't know how exactly the overhead and the complexity of an algorithm in code, which is a thing I generally would think in terms of, translates into scores of gates in an ASIC. This is quite confusing. Whatever, let's just build this one. I think it's at least going to be fun. So I think I just need to concentrate on a couple, and then I would be able to, should be able to copy it over. So let's see, let's build it here. Except remind me, please, what order do I need them in? Output them in sorted order, smallest to largest. Okay, so I want to push small values to the right. They need to be output first. So, let's see here. What am I going to be comparing with what? And what am I going to be saving? Actually, I think this might be a backwards operation. Yeah, probably. I will have my input. I will need to compare it to what was already saved here. Except less than, I need to check. Okay, let's not think about the order here for now. I will compare them. And based on whether or not it's smaller, I will decide whether or not I am actually saving into here at all. That's the first thing I would do. And yeah, I might overwrite. If I am saving, then I'm saving my value that just came in. So it's gonna be this way. Now, that's not all. Because if I have saved the new value, then I want to push the value that was saved forward. So yeah, what's going to be saved, what's going to be pushed forward, I think will need a mux over here. And based on this mux, I will decide, okay, so if this is on, then I am saving. And if I am saving, then I need to propagate not what's saved, but the new thing. So it's going to be this way, right? And the new thing is my... it's a bit awkward. As always, I'll do the wiring later. Right? The new thing will be pushed if I am... Wait. No, I... See, it's the other way around. The old thing needs to be pushed if I have saved something. Yeah, so, and this actually simplifies the wiring. Great. Is that literally it? Yeah, and then this is my new value to be saved, and all I do is I just copy this over, and that's it. Right? Just like so. Is this right? Okay, let's... now I need to make sure that my comparison is in order. So what do I want? I want to save if I am larger. So the new thing... I think it's the other way around. Unfortunately, but it is what it is. So if the new thing is larger, then I will save it here. And I will push what was saved further along. Yeah. Okay. Let's try this for a couple of ticks, I think. So let's just on. Let's copy a couple. A few. Whatever, don't care. Go away. Okay, let's see. So 251. Nothing's saved. Yeah, 250. Oh, wait a minute. My 251 will get pushed all the way over. I didn't quite realize that, but yeah, it will just keep on getting pushed forward. Which is fine. I just need to make sure not to output it too early. Oh, except it's fine. This is exactly what I want. By the time it reaches, I will have read everything, and the thing that gets pushed will be the right one. I think. Yeah, I think so. Okay, let's see if this actually saves... Wait, larger. Oh, see, I got confused again about what order I need them in. Yeah, the larger saves earlier, and then smaller things go forward. So yeah, we have 216. It's smaller, it goes forward. Now it should get saved. And my new value is 20. Yes, and it gets compared immediately, and it's ready to get saved. Perfect. Okay, so 166 is now larger than 20, so it should replace the 20. Yes, and it will. And the 20 goes further and gets saved. Yeah. Cool. Cool, this is working. So now what I need to do is, well, I'll clean this up, and I'll copy it 16 times, and then we'll think about the logics of the rest of this. Okay, so here it is, copied 15 times, slightly cleaned up. Turned out to be reasonably compact. And again, let's just see it at work. Let's see what happens if I just run this. Like, well, I will do it by hand. 20, 63. Yeah, so but now we start getting zeros. Yeah, and this is a... Wait, is it a problem? What's... Yeah, 0 gets pushed through. which is unfortunate. So I cannot quite rely... I cannot rely on new values pushing my old stuff out. But something I can do is I could try to just replace it with 255s. That's one approach that just immediately comes to mind. So normally I would have the input, otherwise 255, and 255 enables once we reach the 16th tick, which actually I should have a decent counter specifically for this. Yeah, 5-bit counter. We can use 16 from here. This is a quick and easy solution. Let's see if this will actually work. I still don't have my output enabled, but whatever. Actually, why not? Might as well enable it. Let's see. So it gets sorted, which is great. And now, wait, I still see a 0. Oh, but it's not this tick. It's not enabled yet. We are going to enable the output next tick. We're going to change the mux and everything is going to be okay. Yeah, 20. And we're saving 255. Yeah, and then my array fills up with 255s and the output is all right. Perfect. Well, that's it. Pretty expensive still. 1460 and 394. Yeah, but it works and it's a very pleasing solution. Honestly, I like this a lot. This is very intuitive and cool. Let's see if it actually works fully. Yay. I wonder if I could do some clever... something more clever than this 255 trick. Probably not. Although... yeah, no, I couldn't. I was thinking maybe I could cheekily subtract a 1 at the start here, then sort, and then add 1 back here. So then when I get zeros, I will get 255s. But of course, that is a problem when I get a 0 that I need to actually sort as part of my array. That won't work. Oh well. I am not sure if I am going to do any better than this. I'm not sure that I'm going to try. Yeah, no. I think proper optimizations for this will involve multi-tick ASICs. So I would have to use multiple ticks to process an input. And I don't want to deal with that yet. That is a world I will probably jump into if and when I explore the delayed RAM stuff. I think that will be an interesting and good, reasonable introduction to the idea of performing a single operation in multiple ticks outside of assembly. So, yeah, I'm gonna say this is it for now. For Delicious Order, of course. Final ASIC. Catching Rain. Let's see. I expect this to be probably more complicated than sorting, because we essentially need to do a lot of comparisons again, but this time we need to do them twice in kind of 2 different ways, right? We need to find for each of these, just to remind you of the algorithm, for each of these columns we need to find what is the highest column encountered so far from the left. And then, once we have read everything, because before we have read everything, it is in fact impossible. We need to establish the highest column seen from the right for each of these. And in assembly, of course, I do that in 2 passes. I just read everything while simultaneously computing the highest from left. And then, once we're done loading everything, I do another pass where I compute highest from right, and I also do the sum. I calculate the sum at the same time, simultaneously. So what do I want to do for the ASIC here? I mean, I have a feeling it's likely to have a similar structure to array sorting. Like, I expect to also have a bunch of registers, I think. It's even the same size, I think. How many columns is this? 16. It's not 15, it's 16 columns, which this one makes more sense. But actually, the numbers involved are probably going to be pretty small, right? So we have 1, 2, 3, 4, 5, oops. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like 10 or 11 at most? Or do they even go as high? So let's see, 1, 2, 3, 4. I'm marking them, you'll see why. Let's run this. Let's see what options we get. So 1, 2, 3, 4, 5. This is 6. Do they get even higher than 6? Do they even get higher than 6? So this is 5. What? You're broken. I'm not broken, you're broken. How did I managed to break leg at some point. Apparently. Or the program, or something. I don't know what happened. Okay, I'll be right back. No, that was a bug. It's all good. But it doesn't... Yeah, we can just see, even with it flashing by, you can see that it doesn't get above this line that is 6. Right, the tree gets pretty tall, but... Yeah. Maybe something flashed over here that was 7, but I think it's actually up to 6. And numbers up to 6 are just 3-bit numbers, so that will be pretty cheap. Yeah, 3 bits are nothing. 3 bits, I can work with 3 bits. Okay, so let's say we're back here. So let's say we have our registers for each column, and let's just assume we somehow loaded everything into them. So each register has the height of the column that it corresponds to. What do we do now, and how do we come up with the actual solution? There's one obvious statement, is that in an ASIC I can do anything in one tick. So once I have loaded everything, and I do need to load all of them, at some point I need to have all of them saved. But once I do, I can just immediately calculate the output. I can just build a contraption that will take all these inputs, analyze them all at once in one tick, and then output the result. What would that be? So I would need to have one line. If I'm assuming I'm not doing any pre-processing, so I'm just loading them, and then I start thinking, then I start working. So if I currently have all these values, I would need to have one line going left to right, kind of, and this is the left to right maximum so far encountered. And then I would also need another line going right to left, which would calculate the so far encountered maximum, right? So for each of these, we would have some wire telling us the maximum. And then I would need to calculate actual, I would need to calculate actual water level, which would be the minimum of these two, right? So that would be another bunch of values here. So, this would be water levels. And then I would need to subtract column heights. So yeah, I would also need to go down here and do another calculation in here. That would be the actual amount of water in that column. And then those I would need to add together. Right, and that's my output. That sounds like a lot. What could I do to simplify this? Well, pre-processing doesn't seem like a thing that could help. So even though I am loading these things one by one, I could, for this first pass, for this left to right maximum, I could reduce the number of maximum comparisons I would need to make. And instead of this line, I could just do the calculation step by step, right? When I load a new thing, I know my maximum, I save it in somewhere else, I save it in some register. And then once I got a new value, I compare it to what was saved and then I update. But the problem is, I do need to keep track of the maximums for each column. So even though my comparison could be reduced, I would still need a whole other row of registers that would be saving my left to right maximum values. And I doubt that would actually be efficient. It seems like a maximum component is probably going to be, well, if not just straight cheaper, all the additional logic would probably put us over the line if I were to try to save the stuff into registers. Saving it here and then deciding which thing where needs to be saved. That's expensive. So probably no pre-processing at all. But then what I just outlined is literally the only solution. Well, the only solution for applying the algorithm I'm currently thinking of. There is, by the way, an alternative idea, which I don't think is viable, but I think it's a fun one. It's just a fun thing to think about. What I could do, instead of saving heights to registers or even working with heights at all, instead I could assign a bit to every square in this grid. So what I would have is something like this, right? And then for each column, I would have a column. So this is 6, right? We have a height of 6. And then we would have 16 of these rows this way, right? And loading a new value, I could literally save an analog representation of the column in my grid. So I could save this as my column, enable some of these bits, right? This is a new column, there's another one, here's another one, and so on and so forth. And then I could try to do an analog emulation of water physics, potentially, and try to pour water from the top. And this would, I think it might be possible to kind of implement this as a cellular automaton, where a new state of a cell depends on the state of nearby cells. And like if you have a water cell nearby, to the right or to the left, water tries to spread. If you have nothing to your left, then you go out. If you have nothing to your right, you go out. But I think the real big issue with this is the fact that my actual state, the actual picture that I'm working with, this thing, is dry state. We have solid blocks, we have water, we have air. And actually, kind of additionally, you might want to say that you have nothingness. Although this is essentially air, yeah. So, yeah, again, every square here has 3 states, but if I were to try to represent them with bits, it would be 2 states, and that's a problem. I won't be able to tell apart some 2 things. Either I won't be able to tell water from solid blocks, or I wouldn't be able to tell air from solid blocks, or something like that. So yeah, this is an issue, unless I want to use, of course, unless I want to use double bit storage for each cell, but that's way over the top, and overall this is ridiculous. But it's a fun little idea, which I think could theoretically be implemented. Just have a physics engine emulated with wires. Going back to this setup with a set of registers saving height, I've actually been sitting here a little while trying to come up with ways to improve this. I haven't really focused much on multi-tick options, but for single tick, I must say I really don't see anything. There were a couple of lines of thought that seemed promising at first, but ended up leading me nowhere. Actually, one of them, the first idea I had, and this took me a little while to figure out. Actually, it's kind of curious. So we have these lines, right? We have left to right max, we have right to left max, and then we have the minimum of these 2 maxes, right, for each register. And this seemed redundant. It seemed like this thing can be reduced, and in fact, it kind of can. Let me pull up the whiteboard. So what this value is, and this is really the only value we need for further computations, right? We don't use these maxes for anything other than computing this line, right? So all I really need is this, and what it is, the value here, it is the minimum, right, of these 2 things, and these 2 things are themselves maximums. So I have maximum. The first one, the one left to right, this value, is going to be a maximum between our current register and the previously computed maximum, right? So that's just a rolling maximum. So what this is maximum between register and right max. Right? And the same thing applies to the other side, except now it's going to be maximum between register and left max. Right, so this is our formula, and this uses 3 maxes. Well, I mean, 2 maxes in the minimum, but they are essentially the same thing. But this is actually equivalent to a formula that looks like this. Register minimum between R max, L max. There's an intuition for this. Both these formulas are essentially levels of water at point. So for every column, this is kind of the level at which water will be at that column. And the way this one computes it is it looks indefinitely far to the left. It finds the highest column. It looks indefinitely far to the right, or well, this is actually flipped slightly. It doesn't really matter, but looks indefinitely far to the left, indefinitely far to the right, finds highest columns, and my water level cannot exceed those columns. So this is what this does. But this thing, it is strictly equivalent, but in order to compute my current water level, it kind of tells me, first of all, if I am a very tall column, then my water level is essentially at the tip of that column. So you can imagine just like a tiny puddle on top of the column. Or if I'm not in a super high column, my water level is going to be that of my lowest neighboring water, right? So what this is, what these values would be, are the values of water height to my left immediately and to my right immediately, and the highest or the lowest. My lowest neighbor is as high as I can go, right? I cannot be higher because I would flow over. I don't know why I explained all this, because I'm not actually going to use this, and also this can be proven just arithmetically. These things are equal. But the important part is, what I wanted to say, is that this uses 3 maxes, while this thing uses 2 maxes. And I thought, okay, great. This is a reduction. I am going to use this. But, curiously enough, while this thing is true, it is a true property of every column, of every value in here, of every value at this point. It is not actually usable for computation. It is not computable. So this is a prop and not a function. That is because, imagine I am somewhere in the middle, so I'm right here, and I'm trying to compute my level of water. In order to compute my level of water, I look to the left and I look to the right. And I see the levels of water there. But, of course, in order to compute the level of water to my right, over here, I do the same thing. I look to my right and I look to my left. So in order to compute this, I need to first compute this. And in order to compute this, I need to first compute this, thus creating a circular dependency both in arithmetical formulas and in circuits. And yeah, this doesn't work. Even though, again, this is a true statement. This is a correct formula. So that's kind of a curious encounter. Yeah, to be entirely honest with you, it still feels like this thing, if I were to implement it, should somehow magically stabilize to the correct answer. And maybe even, like, in Turing Complete, this is definitely not going to work, because we have a dumb check for self-dependency for circular dependencies. Even if in something like this, there's actually no conflict happening here, right? We have this on, therefore this OR must be on, therefore this thing must be on. It feeds back into the OR and it's still on, right? So this wire should just be on. That shouldn't be a problem. But of course this check prevents us from doing that. But I feel like if maybe there was no such check, and if I were implementing this in Minecraft or somewhere, it might flicker and then stabilize or something, because it should, but I'm not sure. Okay. I've been sitting here a while, and I went so far as to implement a 3-bit maximum component, and it costs a whopping 25 gates. Well, at least my implementation of it, which is a fairly naive one, you know, just a mux with a comparison. Maybe this could be, probably it can be reduced. But still, I don't imagine I could reduce this by that much. Maybe down to 20 or something. And even at that point, this is prohibitively expensive. Like, for my idea, with a triple row of these maxes, what we're gonna have is we're gonna have 3 for each saved value for each column. And then this is going to be 16 times repeated. So this is 4, 8, 12, 16. So this is just the maxes. And this costs an arm and, more importantly, a leg. This is not going to be much cheaper, if at all cheaper, than my full solution using a Turing Complete architecture and assembly. Because I'll still need to remember the values over here. I'm I've kind of transitioned to vertical representation since then because it seems more natural. As I'm still gonna have to save the values, and even more importantly, and this is going to be crazy, what I'm gonna have to do is I'm going to have to perform subtraction here. I will need to subtract the actual value from this result, so that'll cost some for each column. And then the worst part is I'm going to have to add all these up. And that basically means I need an adder here, then I'm gonna need an adder here, then I'm gonna need an adder here. So I'm gonna need 8 adders in one row. Then I'll need to add those together, and that's gonna be 4 adders, right? Actually, is that right? Is it 8? That doesn't seem right. Yeah, that's correct. I'll need 8 adders here, then they will lead into 4 adders here, which will themselves lead into 2 adders, and then there's going to be 1 more adder. And even though these are not full adders, I mean, they are going to cost a bunch. So yeah, I think we might well get up into the 2000s with this solution, with this approach. And at that point, I don't see the point. Pun not intended. At that point, it's not better than using leg. So that led me to consider a new approach, a different algorithm that would hopefully be more ASIC friendly. And I believe I have one. It's actually one I think I already considered when I was first writing the solution for this just in leg, in assembly. But somehow I failed to make the final jump, the final leap to making it actually work. And I just decided it wouldn't be viable. But now on second thought, I think it actually looks good and probably even better than what I have in terms of assembly. So the original idea of the ASIC we just discussed was the problem that, or the original problem really of that ASIC was the fact that for each column, I would have to copy the exact same thing n times, right? I would need all these maxes and I need all of them to be in my circuit at the same time, and I cannot reuse the same max over multiple ticks to get new results. Now, I don't think I could prove this in court or formally really defend this position, but it seems like really the issue here is the space complexity of the algorithm. It seems like this has to do with the fact that I am, in my original solution in this assembly, and well, in the approach in general, I am saving a bunch of things to memory to be reused later. In addition to RAM, which I think is still going to be necessary to save. It's still going to be necessary to save all these column heights. I am also at every column pushing the highest, the left high, right, the left high value. I am pushing it to stack. So once I'm done with this first left pass, I end up with a stack that is full of 16 values of these left highs. And this is a space complexity, right? This means that I am using some literally space on my, I guess, chip in this case, to save my values while the algorithm is running. But for an ASIC, what this means is that I need those values to exist somewhere. And in order for them to exist, as we just found out, I need all those maximums copied a number of times. So what I tried to think about is how could I reduce the space complexity of this algorithm? And that means just making the algorithm more forgetful, you know, don't keep as much state, try to calculate as much as you can at every point and do some eager computation. And that was my first approach. I believe I even started writing that program where instead of just saving these highs to stack for further processing in the next loop, I was actually trying to calculate my water levels from the start, from the beginning. And this is possible, and it does kind of work. I can still keep track of left high, except instead of pushing it to stack, I can just have a single register that contains it, that just, you know, saves the value. And I go left to right, I read a new value, and every time I just assume that there's gonna be something on the right to keep the water from flowing out. And so the actual water level at this point, I already assume to be left high, right? So this approach works all the way up until here. And at this point, when there is no longer a high wall to the right, and we start overflowing to the right, it kind of breaks down, and that is where I lost my steam, basically, in my first attempt. And I decided, okay, this is a problem, because in order to detect the point where I will overflow to the right, I first need to go all the way to the right and compute from the right. But that is not actually necessary. What I can do instead is I can try to keep track of whether or not the stuff I added up so far is legitimate. So when I have, say I'm here, I go to the next one, +5. I have my left high, this is this, it's gonna be 6. And I add, but I'm still not sure if it's going to overflow to the right. So it's kind of not legitimate. This is a guess at this point. So I go again, I go to the next one. Still, I make the guess. I make the guess, I just don't finalize it. I'm not sure if it will actually work. I go to the next one, and still I don't see a left high. I don't see a new high. So I make another guess. I go +2. I just assume we're not gonna overflow. But then I encounter this, I encounter the right column. And at this point, I am already certain that this water will not overflow anywhere. I know that we have a full, complete lake, and I can finalize it. I can add it to my actual result. And this is, I can go this way from the start. This does not require me to save pretty much anything. I just need to save one value, which is this high. And I can go all the way, except at some point at the end, I will not be able to finalize, right? So over here, I will add my, well, actually, I will add 5 here, and all 3 columns here will be assumed to have a height of 6, right? I will add them up, but I will realize that I ran out of columns. And once I ran out of columns, I will need to check whether or not my final guess was finalized, whether or not I actually encountered a final high column. And if I didn't, that is when I can go right to left. So basically what this entails is I pretty much just establish the highest point. I calculate left to right, and this is legitimate because it will be finalized. Then it kind of goes higher, but that gets erased because it doesn't get finalized. And then at this point, I go right to left. I will need to keep track of the pointer to the highest column so far encountered in order to know when to stop when I'm going right to left. But still, this is going to be much lower space complexity because all I need to keep track of is, well, this pointer, which is just one value, and the current highest column that I assume is supporting my water. And the 2 passes are actually going to be exactly the same, right? I go left to right, trying to finalize, and I go right to left, and I do exactly the same. I try to finalize. So at this point, I won't be adding anything, but at this point I will actually be adding 3 because my high is going to be at this level, at the level of the small column. So I'm gonna limit myself to this basic explanation, and I won't bore you with the details of implementation, but at first I want to try to implement this in assembly, and we'll see if it works, and I'll be back with it. Done. I think this works. I haven't fully tested it yet, but it seems to run fine. So just like I explained, we keep track of the highest thing so far encountered, and it's no longer left high and right high, it's just the highest on this current pass. We also keep track of the pointer to the highest thing encountered, to the highest column encountered. And this is an important part. I have a result, but I also have an accumulator. And this accumulator is going to be the value that's not yet finalized. I'm going to keep adding water, but I'm only adding this water to the result once I have encountered a corresponding wall on the side that I'm looking for at this point in time. So yeah, just like I explained, we have the first pass. It will go all the way. And what happens, we load everything into RAM, we load all column heights into RAM, and at every point we try to update our high. If we encounter a new high, we save it to the corresponding register, we save the pointer, and importantly, we add the accumulator to the result. So this is finalizing the water, the collection. And we also reset this accumulator because, of course, it is now 0. And then I do the simple thing. I update my accumulator with my new values of water. So notice, this happens every time. So I just constantly update the accumulator. Now, once I'm done here, once I have loaded everything and I have updated everything, I reset my highest position and I do a pass to the right, which, oh, actually, this might not be right. Well, we'll see if it fails. I'll fix it. But this pass is pretty much just always there. And this is a pass going right to left. It does the exact same thing, except now, well, first of all, it can add immediately to the result because I already know that I'm going to encounter a high to the left because I've already seen it. But more importantly, it only goes down to the high pointer, to the highest encountered location. So that's about it. Hopefully that haphazard explanation makes some sense. And let's run it and let's see if it actually works. I think this might not actually work if... yeah, it might do an extra pass if high pointer is equal to pointer. That'll break, but let's see. Actually, no, it seems to work. Perfect. I guess it just goes into 0. Because it encounters the high immediately, but because the high is subtracted from RAM, or vice versa, it's zeroed, so the result doesn't get updated. Cool. I wonder if this is actually more efficient than my original assembly solution. Let's take a look. So this is 185 ticks. That's what I actually care about, right? Oops. Versus, let's try hard min. 185 it was. And now we're gonna be at 189. Yeah, slightly better. Cool. But more importantly, now we're no longer using stack. Not at all. Well, right here I'm just saving a temporary variable to stack, but that doesn't matter. So the space complexity of this is these 4 registers. That's all. Well, actually RAM as well and the pointer, but that's fine. So yeah, this algorithm is forgetful, and I think I should be able to just write an ASIC that works tick by tick and implements just this loop, which is a single comparison. Right? Yeah, it's just this one comparison that needs to happen. And that will save me 16 copies of the same thing. Let's try it. Actually, I just realized something else. I don't even need the pointer to high. I can keep track of something else. And this is especially useful because in an ASIC, resolving a pointer is an expensive operation. It's something I would preferably want to avoid as much as possible. So instead of trying to save how far I need to go, all I need to know is that I need to go, when I go right to left, I need to go only as far as I can until I encounter the highest thing from the left. Right, so I don't need to actually remember this pointer, I just need to remember this height. So now instead of resetting this high, right, I used to have high equals 0 here, I keep it, I called it left high, and then I start working with a different high, and I continue until I find one that is equal to my current high. Right, so until I actually reach it. So yeah, that saves me the necessity to resolve pointers in an ASIC. That's great. And it works. I think the most interesting challenge for this ASIC is going to be the emulation of RAM, and more importantly, the ability to kind of turn around the way, the order in which I read the inputs. So they come in one by one, left to right, and that's fine for the first phase. I'm going to be doing immediate processing on all of them greedily, as we've just discussed. But then, once I reach the end, I will need to start from the end and go back. And in an ASIC, where we don't have RAM and I cannot just move a pointer, well, I mean, I could implement it, but I would prefer to avoid the unnecessary gate expenditure. In an ASIC, this is going to be an interesting challenge, because if I just have, wherever that is, just have a large delay line, no matter what I do, it's going to be in the order it is, right? It's going to be in the order it's going to be. As we read it, it remains a queue, and it doesn't matter how I try to cleverly turn them around and loop it onto itself. It doesn't matter what I do, I cannot reverse it. I cannot start reading this value first, then this one, then this one, then this one, then this one. So I think what I'm going to need to do, if I want to use the delay line approach as opposed to, well, instead of a RAM or some kind of batch of registers which have addresses and stuff like that, I think what I'm literally going to have to do is I'm going to have two delay lines going in reverse in opposite directions. And at some point, once I reach the end, once I have read everything, what I'm gonna have to do is I'm just gonna have to copy the values down, just push it all down, you know, the entire thing kinda goes down and proceeds to the left. So it comes in, it goes this way, it reaches the end, gets pushed down, and starts going that way. And this is the only way I see to turn... yeah, to turn my order around. Actually, now that I say it, perhaps there's another way. Perhaps I could implement something like this thing would be connected directly to here, and it would somehow jump the queue, and then this thing would need to go all the way back here, and so on and so forth. But that doesn't save me anything, I don't think. It's going to be... Nah, I played around with this for a moment, and yeah, it's some kind of setup like this, except I would need switches because I would need gray pins in order to have no short circuits, because this actually short circuits. And yeah, I would also need this to be gray pinned in order to be able to jump forward. But overall, I don't know if I even want to do this. It's hard for me to estimate which approach is going to be cheaper. It seems like this might be cheaper, because here I use a pair of switches. Wait, actually, no, it's 4 switches. Yeah, nah, I think it might even be the exact same cost. But for this one, this is literally all I would need. I would need switches going down, and I would also need switches here in order to be able to jump down. Or rather, these would kind of need to be one-way things, you know, of this type, except for 8 bits one way. So okay, let me try to implement a bidirectional delay line, and I'll be back with that. I must say, this turned out quite nicely. The component has a pretty neat internal structure. But first, let me talk about the just general API of it, the way it works. We have, so this is literally a bidirectional delay. This is a single component that is a delay that can go either way. It can go this way or it can go that way. Which way it goes is decided by the 2 inputs on its top, right? We have forward and backward. So this light blue wire means they go forward. The dark blue, as I've been calling it, goes the other direction. And so if we just had a constantly on blue wire, this would just be a single delay going that way. If we had a constantly on dark blue wire, we would just have a single delay line going this way. So that's already quite neat. And this is actually, I believe this is the first time I use bidirectional pins properly for their actual, well, I'm not sure if this is exactly their intended use, but it's an interesting one. So yeah, this thing just goes both ways. And kind of more interestingly and more importantly, I can turn them around at any point. So I can load something and then I can have it go here, 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 here. So it's delayed forward. And then bam, the direction switches and it starts going the other way. And that's especially cool. So I just set up a quick little demonstration here. We just have a clock. So these first few steps, it'll go forward. And then the last few steps, it'll go backward. So if we just watch the signals, we get a 1, then a 2. So let's just focus on this 1 and 2. 1, 2. 1, 2 goes forward. And we're already popping in the other direction, goes back. 1, 2, you can see. Goes back, 1, 2, goes back. So this is pretty neat. I'm not actually, of course, going to use this kind of control. I will have something a lot more elaborate, or, well, we'll see. But I guess let me talk about the internals of this thing here. So this is a 3-bit delay. You can see I have 3 separate pins, and that is actually not by choice. This was kind of forced on me. I would like to have an 8-bit wide wire, you know, the blue kind, the kind you get here, right? But as I realized, it's not actually possible to have and use the bidirectional functionality of the bidirectional 8-bit pin, of the 8-bit bidirectional pin of this thing. And that is because we do not have a bidirectional byte splitter or byte maker. So I cannot do a bidirectional operation with this wire unless I split it into its constituent bits and then do things with them. But in order to split it and then unsplit it, I need to use these 8-bit makers or byte splitters, right? And these things have an inherent direction to them. So I just cannot use this thing at all. So I think it's kind of only intended to replace a directed input-output pin when you have a weird circular dependency issue, but it's not actually usable as a bidirectional pin, which is kind of strange. This is actually the second issue already I get with these 8-bit wires and byte splitters. The first one is, of course, the fact that they do not preserve the enabledness status of a wire of a single bit. So if I had an 8-bit, if I have, I'm repeating myself, I know, but if I have a gray coming in here and then I split it, this is no longer gray, this is now red. So that's another problem. So I kind of feel like multi-bit buses could be improved in this game a little bit, but who am I to judge? Okay, so this is just 3 copies of the same thing, a bidirectional 1-bit delay, and the bidirectional 1-bit delay is lovely and symmetric like this, which it makes sense for it to be symmetric. Of course, it does the same thing no matter what direction it goes. I don't think I really need to explain this, do I? We have just 2 delay lines, one going right, the other going left, and they are enabled or disabled using these switches. In order to switch direction of my travel mid execution of the circuit, I just rely on the fact that my previous signal was saved in this delay component, and we were going this way, it was saved, then we are going that way, and it's updated. Actually, it would be saved in here. Yeah. So that's that. It's pretty simple, pretty cheap, I would say, 4 gates to delay. It's not bad. And overall, our 3-bit delay is gonna cost 12, so that's 12 by 16. What is that? 160 plus 32, is it? So 192 gates we're gonna spend on the delay line, but it's a bidirectional delay line, so I'd say I'm fairly happy with this. Oh, and also one other thing I should mention is I explicitly made it to have 2 pins for forward and backward, even though going both forward and backward is not an option. Just to save on the knots, right? If I had a decoder for each of these, I would have redundant knots. So yeah, I expect them to always be controlled using the same wire, and I expect these wires to be consistent with each other. So now comes the really fun part. Now comes the part that's different to what we discussed before. We have our 16 registers, quote unquote, which will be saving the heights of columns. And unlike the approach we discussed, we do not need to work with these values at all. We don't ever need to load them, we don't care. To me, this is just a stack, literally. So stuff is gonna get pushed onto it, and then stuff is going to get popped from it. And I am only working on the values on these wires at a time. So I think for starters, I'm gonna just build it as an 8-bit contraption, and then we can reduce it if necessary. Okay. Let's see here. What do I want to do first? Well, the first thing that comes to mind is working with my maximum. So at all points, I need to keep track of the maximum number encountered so far. So let's just use, for now, let's just use a max component, an 8-bit max component. I'll set it to constant max, right? Yeah, so it'll constantly be outputting max. And I think it is going to be a circular thing. I think what's going to happen here is we're going to have this input, this is our new contender, but what it's going to be compared to is the previous maximum. So what I'm going to want, I'm going to want a delay over here, and I'm going to want to compare this maximum to kind of itself, right? Wait, why is the output in such a weird spot? Yeah, the shape of this max is strange. Can I? No, I don't. I'm not going to change it, but okay. So this is now my maximum. Is it that simple, really? Okay, let's see if it works. So first I load. Okay, let's load something. Hello? Oh. Need to enable the input. Of course, I'll worry about the control flow later. Let's see. 4. Yes, 4 is the largest so far encountered. 6. Yes, perfect. And now we get a 1, but the 6 is not updated. Well, would you look at that? That's ridiculously easy to make. All right. So next, I am going to want... I'm gonna want to subtract this from my actual input, right? Or rather, I will want to subtract the actual input from the max so far encountered. So let's do a really quick and cheap and dirty and easy subtraction operator. Let's just do add and negate, and that's it. Right, so this is my subtracted value. So this is actually the amount of water I am assuming to be in the column at this point. So now what I'm gonna want to do is I'm gonna want to keep, so this is going to be added to the accumulator. Let's worry about the control flow on the accumulator later. So I'm gonna be adding this to something, and I think, yeah, I think I just reused the same trick. I wire the adder to itself, and it keeps incrementing. It's gonna be, no, resetting this should be simple enough. Okay, let's check if this works. Let's see. This should actually get us as high or as far as this tree already, with the correct result for water. So by the time we have loaded this tree, I should expect, well, let's just watch it. Let's just watch it. So we get, oh no, I can't. Please show me water. No. I can't see the water, and okay, let's try to remember it. So we have 5, 2, 1, 5, 2. Okay, so this should be 0, yes, 0. Then we should have 5, yes. Now we should have 7. Now we should have 7. Plus 1, 8, yes, plus 5, that will be 13. Yeah, look at that, it works. Already, simple as that. So this is already good for the accumulator, but I also need to be able to commit my result and reset the accumulator. How do I do that, and where do I commit it? Well, I think the actual output is going to be the exact same setup. It's going to be this kind of adder, which keeps adding to itself. And I mean, this is kind of a register with additional capabilities for addition. Pun not intended again. Yeah, it's gonna be like this, except this should mostly be a 0. Should mostly be a 0. Unless... yeah, this is just a switch, not a mux. It's fine. This should be a 0 unless we have encountered a new high. So it looks like I'm gonna have to unfold this min-max. Yeah, and yeah, I would have to get the guts of the comparison out of it. But for, oops, no, that's not what I wanted to do. This is not it either. For now, again, since we're doing the first quick dirty approximation of the circuit, let's just add a comparison on top. So will less unsigned, do I want less? Wait, I can't be bothered. Let me just check what I have in my assembly. Less than. Nah, that's not the right way to be lazy. That doesn't actually help me. What kind of comparison do I want? What do I want to be less than? What? If I have encountered a new high, so a new high means my old thing is less than, input 1 is less than, so if my new thing is less than, my old thing is less than my new thing, then switch. But also what I'll want is, I'll also want this switch here, because I want to reset the accumulator, right? So something along those lines. Let's see. Let's see what happens. So at this point, well, we've actually encountered, yes, we've encountered a new high. It's a 4. That's great. We are saving everything, but so far the everything we're saving is 0. We should encounter a new high, yes. We encounter a new high that is a 6. Again, we are saving, but we are saving nothing. And now there will be no new high, but we are saving to the accumulator. Wait a minute. I think I want this... I want this inverted, right? Because I want the accumulator to actually work unless new high. So start again. 6 we've encountered. Now we see this thing. We have saved the 5 to our accumulator, but it's not committed yet. We go forward. This is still not a high, but we have saved the 7. And now we'll encounter a high. Except we don't. And that is... Well, that is correct. I think I want a less than or equals. Let me do a less than or equals real quick. Yeah, just a quick dirty fix here. Just an OR. Obviously, I will clean this up later. So let's see if this works. I wasn't following. So nothing, nothing. Add 5, 7. Add nothing but commit. I haven't committed. That's not good. I think my switch is in the wrong spot now. It's not that I want nothing at this point. I want nothing at the next step. Right? This is gonna be better. Okay, third time's the charm. Is this the third time? I think it is. So nothing, nothing. 5 saved. 2 saved, 7. Nothing but commit. Yes, committed. But now add 1 and reset accumulator. Yes, accumulator reset and 1 save to the accumulator. Perfect. Okay. I think this is working. Except 24. Oh, yeah, 24. I thought it was 42 for a second. Yeah, 24 seems about right. What's 24? 5, 5, 5, 15, 20, 24. Yes, yes, the size of these two puddles is 24. So that's cool. And the final thing I need to do is I need to detect when I have reached the end of my stack, and that'll actually be easy to detect. This wire will light up because all my numbers are greater than 1. actually, that's not right. One of these wires will, at least one of these wires will light up. I can do... can do a triple OR, maybe. It's probably the easiest way. Right, so this means I have reached the end of my stack. And at this point, I will want to... First, I will want to flip the direction in which I'm going. In which my stack is going. But I, kind of more importantly, I need to... I need to flush the accumulator, because the accumulator was wrong. Yeah, so... Over here, I probably want an OR, right? I want this not to be enabled by an OR of these things. Something along these lines, right? This and this. Yeah? Let's see if this still gets me to 24. 7, 24. Yeah, it still works to 24. Then actually 25 should be no problem. And now we won't commit. Oh, well, the delay is not even working at all. Okay, now for the delay. I think this is just the matter of adding a 1-bit memory here. And oh, I want my 1-bit memory to start out enabled. Actually, I could use a decoder. Something like this. And then by default... Okay, this is messy. This probably needs to be improved somehow, but let's just finish this real quick. I need to save a different value to it. So a different value will be an on. Save enabled. And it will be enabled by this OR. So once we get something, we will be saving the on, and then it will immediately flow back out, so this OR will be disabled. Which doesn't even matter, I just need it to become on. Okay. Yeah, and don't forget to connect this. Let's see if it works. Wait, is this right? Yeah. Yeah, this, I think this is correct. Let's see if this works. I will also, man, I also need to, I completely forgot, I need to detect when to stop. Oh, man. Oh, no. Yeah, this is a pain. So, I won't stop the actual circuit. I won't be stopping anything in here. I think in order to stop, I just call the return. Right, I just return. So my return value is going to be exactly this. But it's going to be enabled. First, we need to be going backwards. So it's an AND over here. We need to be going backwards. And we also need to have just encountered. Oh no. Oh no. I forgot about the high now. Oh no. This is bad. I need to... oh man, this is getting more and more complicated. I need to save the high somewhere. Do I probably want it saved separately. To register somewhere. Oh man. Okay. Well, again, let's just try a quick fix. Although this is getting a bit too messy for quick fixes, but still, let's just put a register, just plop down a register over here. And actually, once I'm starting to go back, I want to do two things. first I will want to disable this. I will want to reset my min-max. Right, so min-max needs to go like so. And it needs to be disabled, which means a not. Over here. No, yeah, I know. Don't worry. Something like this, I need to reset my min-max, but also I want to save this min-max to a safe location, that is this register, and save. I can have it constantly loaded, that's fine. Actually, let me use it cheaper. It doesn't matter. This will all be redone regardless. Yeah, so now this thing has my high from the left pass, and every time I will want it compared to my input. Ooh. And then I output. Is this right? Honestly, I'll be surprised if this works on first try. This is the kind of spaghetti you don't get to work. Don't get to a working state on your first try, but let's run it. Looks like I'm the spaghetti master. This is literal spaghetti, isn't it? It's even spaghetti colored, kind of. You have literal wires just all over the place. But this is cool. This is cool. This is pretty efficient. You know, this is already less than half of what I had from just putting down maximums. And I am using full components. I'm using a full adder to add 2 3-bit numbers. And yeah, a lot of other things like that. I'm using double comparisons and equals, a less than or equals, and min-max separately. So yeah, there's a lot of room for improvement here. But that's the gist of it. Guess it's time for me to improve. 2 hours later. I think this turned out pretty well. Looks good. Pretty cheap. 381, 116. It's still quite a spaghetti, to be honest, down here, but I guess that's to be expected for a reasonably complex, not quite symmetrical problem. So yeah, this is the exact same schematic that we just built using large components and a lot of weird wires. Except everything is now stripped down, so this is a 3-bit less than equals, 3-bit mux, and I know that I only add up to 7 bits, so we have 7-bit switches and 7-bit stuff, so on and so forth. Don't know if I even need to explain this. I guess let me go over it real quick. So we still have this thing up here, we've already discussed that. We have 3 gray loops, and these are kind of saved. Well, actually, it's either 3 or 4, depending on how you want to count it. These are saving our state. So the first thing is the highest encountered value. And you can see it's just constantly powered on, except when a red control event happens, which is when we start going backwards, right? So this is this one. Then it's reset once on every run of the entire circuit. So yeah, this is just a mux with a maximum or with a comparison wired into it. So if essentially these two are a single maximum, there's a delay and so on and so forth. Next up, we have the next part of the state is this tiny little register up here. This is the register that saves the highest value from the left to right run in order to be reused on the right to left run. So that's that. Every time we load a new value, it immediately gets subtracted from the maximum. So that's that. Then this loop is the intermediate accumulator. Again, this is just an adder into a switch into a delay. This switch can be flushed in one of two circumstances. Either we haven't encountered a new high and we are there for flushing and committing. So that's the yellow event over here. Or when we are going back, the accumulator is not valid and it just gets flushed but not committed. So that's the second loop, and the final third or fourth, depending on whether you want to count this as a loop. The fourth part of the state is just the final result accumulator, which will be fed directly into the output. Same thing here, pretty simple. It's just an adder with a delay. So this is only counting up, and it cannot even be flushed. It'll just push its output to our, well, push its result to the output. And yeah, the white wire decides whether or not we're going backwards. So that's this, and we have the comparison using 3-bit equals, the comparison between the newly read and the saved last time value, the previous high value, that allows us to actually finish execution of the circuit. So that's that, and let's run it. You can kind of see, especially on, yeah, like here, on things where we need to backtrack far away, for where you need a long backtrack sequence, you can kind of see the pattern going there and back, bouncing back. It's kind of hard to spot. Yeah. Well, it all works. Let's just run it for 128 problems and see our final results. Score 530. It's pretty cool. Worst test 34. Wait, how did I get a tick score of 30? I don't understand. At most, I should be doing 32 operations, right? Going all the way there and then all the way back. How did I get 33 or 34? I'm not sure. I'm not gonna try to understand it. I don't really care. But okay, score 530. This actually turned out to be much more efficient than Delicious Order, even than the sorter. And I expected this to be more complicated than the sorter because it's kind of somewhat similar tasks to me somehow. At least they seemed that way until I actually implemented the solution. But yeah, that marks the end of my ASICs buildage for the entire game, except one final level, AI Showdown.